Alright, hello everybody. So today we're going to be talking about vectors. And the motivation is that we have two different types of measurements. So our first type of measurement, I'll say here, is something like temperature or mass or length. And our second type of measurement is going to be something like displacement or velocity or force. Okay, so you might wonder what's the difference between these two categories, and the difference is for the first category, these tell us how much, which is the same thing as saying that these things tell us how much magnitude, right? So they just give us an amount, and we're going to call the amount a magnitude, right? So we can look at the second category and we can say, well, the second category also tells us how much, but it also tells us which way. Right, so it tells us how much, but also what direction we have. So I'll say that here, this is our magnitude, and this is our direction. Right, so we're looking for things that have both magnitude and direction, right? So if you say we have velocity, then you're not just saying the speed. Speed would just be a magnitude. So let's say you said you were going 50 miles an hour. We don't know what direction that is, so that's just speed. But if you say velocity, that means you're going 50 miles per hour. Let's say you're going 50 miles per hour west. So that actually has a direction to it. So we can call it velocity, right? So the things in this category have both magnitude and direction. And we're going to call those things vectors. So I'll say here, the term vector is used to indicate that a quantity has both direction and magnitude. Okay, right. So we're just going to call these things in the second category vectors. I'll say here, in Calculus 1, we learned how to find velocity of objects moving in a straight line. In these cases, a positive velocity would indicate that you're moving forward, and a negative velocity would be moving backwards, right? Or left and right. So the issue is left and right is fine if you're working in one dimension, but if you're working in higher dimensions, you don't just have left and right. You just, so let's say you're working in 3 dimensions. Well, what's left and what's right, right? That doesn't quite make sense. So we have to come up with these things called vectors to describe the direction in which we're moving. Okay. And I'll say here that our geometric view is going to be that we often represent a vector with an arrow. Okay. So I'll say here the length of the arrow represents magnitude and I'll say also that the arrow points in the direction of the vector. Okay, so, right, of course, so whenever we have a vector, we have both the magnitude and the direction, so we draw a picture of it, and the direction would be the same as the direction of the vector, and the length corresponds to the magnitude. And I'll say here we denote vectors with arrows over their names like V hat or U. Right, so we just draw a little arrow over the letter, and that means that it's a vector. Okay. And now we want to look at the case. Let me erase this left-hand side. We want to look at how we can draw these vectors. Okay. So, right here, suppose a particle moves in a straight line from point A to point B. Then I'll say the corresponding displacement vector V has initial point A and terminal point B. Right, so if we, and also I'll say, we indicate this by writing, so here, V, the vector V, equals the vector from A to B. Right, so we can write it this way. And all of this is to say, well, let's say we have our points A and B. So I'll draw our points A and B. Then the vector going between them is going to be this vector. V, which is going to be equal to A, B. Right, so if we draw a vector between the 2 points, that's going to be the displacement vector between the 2 points. And I'll say here, let's say we have another vector going from C to D, and let's say that this is our vector going from here to here, where U equals CD. So we can say here that, well, v and u, well, they're going between different points, but you can say that they fundamentally look the same, right? So if I might have drawn them a little differently accidentally, but you see that their length is both the same and their direction is also both the same. So if they have the same magnitude and the same direction, those are the two things that define a vector. So we can say that v and u are actually equivalent vectors. So I'll write that down on the next board. So it doesn't matter that they start and end at different points. If they have the same magnitude and direction, then they're equivalent vectors. So I'll say here u and v have the same magnitude, meaning the length, and direction, so they are equivalent vectors. Okay. All right. So those two vectors are the same, and we will write that u equals v. Right, so the two vectors are equal. So we'll just write that the two vectors are equal. And I'll say here in red, a separate note is that the zero vector we'll write that as 0 with a little hat on top of it. That's going to be the zero vector has length 0, and it is the only vector without direction. Right, so if you look at a vector, we said it has to have both length and direction. The only exception is for this zero vector here. Okay, so our next section is looking at combining vectors. So that's what we've got to do next. So all the Chapter 12 material is certainly very relevant if you are going on to Calculus 3, because Calculus 3 is all about doing calculus in 3 dimensions, and these vectors come out quite a lot. So I'll say here the next thing is on combining vectors. And certainly just a lot of things are actually vectors, right? We said velocity, force, displacement. There's a ton of examples of vectors, so they're very useful. And we're looking at combining vectors. So I'll say here, suppose a student walks from, and these are building names, I'll say first building is going to be Lockett, to the second building, which is going to be Tiger Stadium, and then to the third building, which is going to be the PMAC. Right, so we're walking between all 3 of these buildings. So what's going to happen here is we start at point A. Let me draw this. So we start at point A, then we go to point B, and then we go to point C. So what we're doing here is we've got our first vector, which is where we're going from A to B. So I'll draw that. Let's draw that as U. And our second vector is going from B to C. Let's call that V. And I'm putting hats above them to indicate that they're vectors. Those are displacement vectors, meaning the distance between the two, but also the direction, right? So displacement is both distance and direction. So this is the displacement vector between A and B. Okay. And I'll say here, the students must draw a third dotted line going this way. And I'll say here, the students displacement vector is, so it's going to be AC, right? So the total displacement, we're looking at the total displacement. So you're going from A to B to C. So in total, you're going from A to C. So the displacement vector is AC. It's the distance between, or sorry, the vector between A and C. And it's going to be the vector AB plus the vector BC. Right, so we're looking at combining vectors, so we're adding the two vectors here. Okay, and AKA, let me draw in a different color here. AKA, so another way of seeing this is that U plus V, the vector U plus V, which is the total vector here, is equal to the vector U plus the vector V. Right, so that's the other way of writing that. But we want to know in general, how can we add these vectors? So I'll write that down as our next section. Or I guess I'll write it here. So I'm going to use the Roman numeral 1. This looks like an I, but it's the Roman numeral 1. And I'll say vector addition. Okay, so that's our first section, is vector addition. Okay, so if U and V are vectors positioned so that the initial point of V lies at the terminal point of U then the sum U plus V, so vector U plus vector V, is the vector from the initial point of U to the terminal point of V. Right. So let's unpack exactly what I wrote there. So we're saying U and V are vectors, so we have our vectors U and V here. And I said earlier, it doesn't matter where we draw the vectors, it doesn't matter what the initial and final points are, just so long as the vector has the same direction and magnitude, right? So I've drawn U, and V could have been over here, but I've just moved it so that the initial point of V is the same as the terminal point of U, right? So if we've got this vector and then this vector such that its initial point is the ending point of the previous vector, then actually the way you add these two is just by drawing the straight line from the beginning of the first to the end of the second vector. Right, so that's all that that's saying there. So I'll go ahead and, well, this here, I'll say that this here is called the triangle law because it kind of makes a triangle, right? So I'll draw another example of this. Okay, so that was the triangle law. I erased the name, but that was the triangle law. And we're going to look at an example of how to add vectors. So, well, let's just say first, if we have a vector u and a vector v, then the way that we get u plus v is just drawing this straight line. So this here would be the vector u plus vector v, right? So that's how we add the two vectors, but let's draw two just separate vectors. So example 1 is going to be, so we're trying to find the sum of u and v, and I'll say that u is this vector and v is this vector, right? So we want to add these two vectors. So remember, the way we add these two is by first picking the vector u and sticking this vector onto the end of the vector. So what we do here is we take our u, so right, I just redraw the vector with the same direction and the same magnitude, and I'll redraw the vector v as well. So this vector v I'll redraw right here. So that should be the same direction and the same length as our original vector v, right? And adding the two just means taking the vector from this point to this point. Okay, so I'll just draw the line there. So here, the addition of the two vectors is this vector here, u plus v. So again, the way we add two vectors is we take one, we stick it on the end of the other one, and then we just draw the straight line from the start of the first vector to the end of the second vector. That's very important because that comes up a lot. We need to know how to add these vectors. And you can note that, well, this was u plus v. I probably should have rewritten this, so let me just draw this again. So this is u, and this is v. This was u, and this was v. And now let's see how well I can draw this. If I instead draw v here, and then u again, so this was v, and this was u. So if we then draw this line from here to here, then note that this line, so if you look at the top, this was u plus v, so this is u plus v. And if you look at the bottom, we started with the vector v, and then we added the vector u, and that was the same thing. So u plus v equals v plus u. So what I'm saying here is it didn't matter which vector we picked first, just so long as we pick the vector, and then we stick the other vector on the end of that vector. So we did the same thing with v. So we picked v, and we stuck u onto the end of it. They both give us the same answer. Okay. So I'll say here, just like regular addition, the order doesn't matter that you add these in. Okay. Our next section, so that was vector addition. Our next section is on scalar multiplication. Okay, so here we want to talk about, so this is Roman numeral number 2. this is going to be scalar multiplication. Okay. So you may be wondering, well, what the heck is a scalar? And I'll say here we call a number C a scalar to distinguish it from a vector, and I'll say here scalars have no direction. So in the beginning of the video, I drew two categories. The first category was just magnitudes. They didn't have direction, so it was things like speed or mass. Those are scalars, right? Because they don't have a direction to them. The second category was vectors because they had both magnitude and direction. So if we just have a number with no direction, we're going to call that a scalar. So it's just a fancy name for just a number that doesn't have a direction to it. Okay. So our definition here is going to be if C is a scalar and V is a vector, then the scalar multiple C times V, so this is C times V, it's a little bit hard to see what I wrote there, C times V is the vector whose length sorry, I need to erase this, whose length is magnitude of C, so that's just the size of C, or the absolute value of C, so just the absolute value of C, times the length of V. And in the same direction as V, if C is greater than 0, and in the opposite direction as V, if C is less than 0. Right. So if we look at what the statement is, so I just wrote down a bunch of stuff here, but what this is saying is if you have V and then you multiply it by a number C, then we're going to say that the length of the resulting vector is going to be the absolute value of C times whatever your original length was, and if C is a positive number, then the direction doesn't change. But if you multiply a vector by a negative number, the direction gets exactly flipped. Okay. So let me just write down what this looks like for vectors. So let's say that this is our vector. Let's say that this is V. Then if we want negative V, then we just have to flip the direction, right? So this would be negative V, right? The length should be the same. This is the same length, but opposite direction. And if we wanted, let's say, 1.5 times V, then we just draw a longer arrow here. This actually looks a bit longer than that. Let's say that this is 2 times the length of V. Right, so all I did was I kept the same direction, but so this is the same angle as the original vector, this is the same direction, but I just scaled it, meaning I That's why it's called a scalar. You're scaling it. I just lengthen the vector so that it's double the length of the original vector. Okay. So the next section here, so that's how you multiply a vector by just some number. And the third section here is vector subtraction. So we learned how to add vectors, but we also want to know how to subtract vectors. Okay. So section 3 is going to be vector subtraction. Okay. So let's say we have u minus v. We want to interpret what that means. But this is just u plus negative v. So we already discussed what negative v is. You just take v and you flip it into the opposite direction. So if you add u plus negative v, then that's actually the same thing as u minus v. So that tells us exactly how to subtract vectors. So I'll have example number 2 here. And I'll say the example is asking us to draw a minus 2b. And the vectors they give us, this is a, and b looks like this. Okay, so we want to have a minus 2 times b. Now, the first thing we need to figure out is, first, we need to figure out minus 2 times b. So we need to write down what that looks like. So the negative sign means we flip it in the opposite direction, and the 2 means we double its length. So now, negative 2b is going to look like this. Negative 2 times b. That's going to be our answer there. Whenever we... So this should be b in the opposite direction, but twice the length. Okay. Now we need to add negative 2b plus a. Right? So we draw a. If we're adding the 2, we draw a. This is our vector a that I've redrawn. And then we draw our negative 2b. This was a little bit poorly drawn. Let me redraw that. So this was our minus 2b. So we've got a minus 2b. That gives us our resulting vector here in red, which is going to be a minus 2b. That would be our answer. Okay, so that's our vector. Now, the next section here is going to be components of a vector. And this is going to depend on what coordinate system you're in, whether you're in one-dimensional space, two-dimensional space, or three-dimensional space. Okay. So the next thing is components. Sorry. We're done with that section. The next thing is components of a vector. Okay. So we're going to talk about components of a vector. So let's say if we place the initial point of a vector A at the origin its terminal point has coordinates A1, A2 if we're in 2D, or A1, A2, A3 if in 3D. Right, so all that's saying is, well, let me write one more sentence here. These coordinates are called the components of A and we write A equals A1, A2, or A equals A1, A2, and A3. Right, and that's going to depend whether you're in 2 dimensions or 3 dimensions. Okay, so I'm going to say exactly what we mean by this here. So this is the final point, so we're labeling this vector that starts at the origin and ends at this point by the coordinates of the terminal point. So we want to draw exactly what we mean by that statement. So let me do that. Okay. So consider the vector OP below. Okay, so we're going to label our coordinates. So this is going to be the y-axis, this is going to be the x-axis. And then we're going to draw, so let's say this point here, we're going to label the origin by O, and we're going to label the final point by P. Right, so it's going from O to P, and this is our vector. And P, I'll say, is the point 3, 2. Right, so the x-coordinate is 3, the y-coordinate is 2. Right, so we can draw a bunch of other vectors here. But notice that all these vectors that I've drawn are actually the same as the original vector I drew. I've just drawn them in different positions. This one actually looks a little bit different, but these are all the same as the first vector I drew. I just drew them in different positions. So I'll say all of the geometric vectors shown are representations of the algebraic vector A equals the vector from 3 to 2. Okay. So all of these vectors are the same as the original vector, and I said that we label this original vector that starts at the origin and ends at this point by its coordinates. And we just draw these brackets instead of the parentheses. So this notation means that it's a vector, these brackets. So I'll say the particular representation from O to P is called the position vector of the point P. Right? So this was our point, and the position vector of this point is exactly the blue line that I drew there. Okay. The next thing to say here is, let me say here, given the points A, which is going to be x1, y1, z1, and B, which is going to be x2, y2, and z2, the vector A with a hat on it with representation AB is, okay, so now we're going to write out what the vector exactly is in terms of the coordinates of the 2 points. So the way we do that is we take the final point and we subtract the initial point, right? So our vector here is going to be x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. Right? So the way that we find the vector with this representation between the 2 points is just by taking the second point and subtracting the first point. Okay, so we can move on to an example here, right? So this was kind of definition heavy. So we can move on to an example. So example number 3 is going to say find the vector represented by the directed line segment with initial point A, which is going to be 2, -3, and 4, and terminal point B, which is going to be -2, 1, 1. Right, so we've got a vector between these 2 points, and we're trying to find the representation, which is this, right, this. We're trying to find the representation of the vector between these 2 points. So the way we do that is just exactly what we did here. We take the second point and we subtract the first point. So our vector A is going to be equal to, so we take the second x value, -2, and we subtract the first x value, 2. And we do the same thing for the y and z values. So we're going to take 1 minus negative 3. And here we're going to have 1 minus 4. Okay, so we just got to compute what this is. This is going to be negative 4, and then minus negative 3, that turns into positive 4, and this would be negative 3. All right, so this is going to be our representation of the vector between A and B. Okay. So the next thing to talk about here is, so we've already finished the example here, and the magnitude or length of the vector v is the length of any of its representations and is denoted by absolute value of A or with 2 lines. Right, we wouldn't say absolute value. Here we would say the magnitude of A for both of these. Both of these mean the magnitude of A. Because you take absolute value of a number, but a vector also has direction, so it doesn't make sense to take its absolute value. But this is essentially just taking the absolute value of its length. That would be its, well, that's its magnitude. Okay. So I'll say here, we get different things for whether we're working in 2 dimensions or 3 dimensions, so we should write that down. Okay. So in 2 dimensions, we're going to have the magnitude of A equals the square root of its first entry squared plus its second entry squared. Right, so this is the x value of its representation, and this is the y value of its representation. We square both of them, add them together, then take the square root. That gives us the length. And in 3D, you might be able to guess it's very similar. We're going to have the length of A equals square root of A1 squared plus A2 squared plus A3 squared. And this is what we would get. Okay. And if we're adding and subtracting vectors, we figured out earlier how to do that geometrically, but we also need to know how to do that algebraically. So I'll say here with a star, adding and subtracting, I don't know why that's capitalized, adding and subtracting vectors algebraically works component-wise. Okay. So what that means is if A equals A1, A2, so this is the representation of the vector, and B equals the representation B1, B2, then, so we're going to have A plus B is going to be equal to A1 plus B1 comma, A2 plus B2. Right, that's kind of what you would expect, and the same thing works with subtraction, right? So if we had A minus B, it would be A1 minus B1 and A2 minus B2. Okay. And the next thing we need to talk about is what happens with scalar multiplication. So that's also something we talked about earlier. We talked about how to do that geometrically. We want to figure out how to do that algebraically. So to multiply a vector A equals A1, A2 by a scalar C, you multiply each component by C. Okay. So we can write down what that looks like. C times A equals, I said you multiply each component. So C times A1, comma, C times A2. And that would be the vector C times A. Okay, so now we can move on to another example. So for our next example, example number 4, we can say let A equals the representation 4, 0, 3, and B equals the representation -2, 1, and 5. So we want to find part A is going to say the magnitude of A. So we want to find the magnitude of A. So we want to use the formula that we wrote down. So you might want to try just doing this on your own if you want, but if we use the formula that we wrote down earlier right here, we've got 3 coordinates, so we need to use this formula. We just plug in the coordinates into this formula. So we're going to have the square root of 4 squared plus 0 squared plus 3 squared. So that's square root of 16 plus 9. So it's the square root of 25, which is going to be exactly 5. So that would be our answer. Okay. The second part asks us to find the representation of, it's not what I meant to write, the representation of A plus B. Alright, so again, you can try doing this on your own, but if we try to add A and B, then we just look at what we wrote down here. We just add the 2 components, right? So, or in this case, we have 3 components, but we add together each component. So we add together the x components, so the x component of A plus the x component of B. So we're going to have 4 plus our -2. Our second entry is 0 plus 1, and our third entry is -2. Or sorry, that's not what I meant to write. Our third entry is 5 plus 3. So 3 plus 5. Okay. And now we just add everything together, and we're going to get 2, 1, 8. Okay, so that would be our answer. Our third part asks us, part C is going to ask us to find A minus B. Right, so you just take the coordinates of A and you subtract off the coordinates of B. So again, Very similarly, this is going to be 4 minus our negative 2, comma, this would be 0 minus 1, and the third one would be 3 minus 5. Okay, so we add together 4 and 2, that gives us 6. This is negative 1, and this is negative 2. So this is our representation of A minus B. Part D asks us to find 3 times B. Right, so I said for scalar multiplication, yes, so for scalar multiplication, we're multiplying A by 3, so we just multiply each component by 3. So, or sorry, not A, well, in this case we're doing B, but for B, we just multiply each component by 3. So, we're going to have, let me give myself a little bit more space here. So, 3 times B equals 3 times negative 2, comma, 3 times 1, comma, 3 times 5. Right, so we just multiply everything together, and here we're going to get negative 6, 3, and 15. Okay, so that's going to be our representation of 3 times B, and we just have one last part. Okay, so here also the space of n dimensional vectors, or sorry, oh shoot. Okay, I meant to write down part E. I skipped that. Let me write that down before we talk about that. So part E is just going to say we're going to have 2A plus 5B. Right, so we just want to write down what this is. So let's just first write down what 2 times A looks like. So 2 times A, we just multiply all the components by 2. So we're going to get 8, 0, and 6, plus, now we write down 5 times B, so we multiply every component by 5. We're going to get negative 10, 5, and 25. Right, so I just multiplied all the components. And then now we just add together the 2 vectors by adding each component. So we're going to get negative 2, 5, and 31. Right, so that would be our answer there. Okay. What I started writing, which I'm going to rewrite now, is the space of n dimensional vectors is called Vn. Right, so we're just going to call that Vn, and we're going to have properties of vectors. So if we have a space of vectors Vn, then it's going to have to satisfy the following properties. So let A, B, and C be vectors in Vn, and we're going to have to satisfy the following properties. So, or okay, what I meant to say here, and let C and D be scalars, then it's going to satisfy, then we're going to have number 1, which is going to say A plus B is the same thing as B plus A. Number 2 is going to say that A plus B plus C equals A plus B plus C. Right, so we call the first property commutativity, which we expect with numbers, right? If we add a number A plus a number B, then that's the same thing as adding B plus A. So it's not as obvious why it works for vectors, but it just turns out that it holds. And the same thing, this is called associativity. If you add these two numbers first, and then you add the third number, it didn't matter the order you did it in, right? You could have added the first two numbers and then the third number. Okay. The third property that vectors satisfy is going to be that A plus the 0 vector, we can kind of expect what this should be. This is just going to be A. So this is going to be the vector A. This doesn't really look like an arrow. Right, so I usually just draw half arrows, meaning I don't draw the bottom part of the arrow, but it doesn't really matter. Okay, and property 4 is going to be the vector A plus vector negative A is going to be the same thing as 0. Right, so you would expect if you add something to the negative version of itself, it should cancel out and give you 0. Property 5 is going to say C times A plus B equals, you can distribute, so we're going to get C times A plus C times B. Okay. The next one, number 6, is going to say that C plus D times A, you can distribute the other way around too, right? So we were able to distribute a scalar, but you can also distribute a vector. So if we distribute the vector, we're going to get C times A plus D times A. Okay. And property number 7 is going to say that C times D times A is equal to the same thing as if we multiply C by the vector, which is D times A. Right, so multiplying this scalar by A is the same thing as multiplying C times the vector, which is D times A. And the last property, as you would expect, if you multiply 1 times A, you're going to get back A. Right? So you might say, well, all of these should just obviously hold for numbers. Well, certainly they would if we were working with numbers, but vectors aren't numbers, so it's not quite as obvious why all of these hold, but all of these do end up working. And since all of these work, we can call this a vector space. And you can see it's actually quite a lot of things that something needs to satisfy to be a vector space. So we're not going to deal too much with vector spaces in this class. That's more of a linear algebra thing, but if you ever do take linear algebra, these structures are very important. All of linear algebra is just all about vector spaces. All of linear algebra is working within vector spaces, so they end up being very important. Okay, but let's talk about the next thing. Let me erase this first part. Okay, so we have 3 special vectors in V3. So we have 3 special vectors in V3, which, remember what I said here, the dimension of the space is this subscript. So this is going to be 3-dimensional space. So I'll say here, this is 3D. Okay. And we'll give them, so we give them special names, which are going to be I, or that's not what I meant to write. It's going to be I, vector j, and vector k. So those letters are reserved for just these three special vectors. And the reason why they're special is that I is going to be equal to the representation 1, 0, 0. J is going to be equal to the representation 0, 1, 0. And K is going to be, as you would guess, the representation 0, 0, 1. Right, so if we're talking about these three special vectors, they actually have names. And I'll say here, let me use a different color. We call I, J, and K, so all, that's not what I meant to write. So we call vector I, vector j, and vector k standard basis vectors. They have length 1, so the length of all these is 1, and they point in the direction of the positive x, y, and z axes. Right, so that's why they're special, is because they point exactly in the positive x, y, and z directions, and they have length 1. So that's why we give them special names. And I'll say, just as a note, if you're only working in 2 dimensions, in 2D, we define I equals 1, 0, and j. See, I keep writing these hats. These are actually not what I'm supposed to write. We write these. So vector j is equal to 0, 1. Okay. So in 2 dimensions, we just get rid of one of the coordinates. That's how we would write it. And the reason why these are important, so the reason we went through all the trouble of defining these, is that the standard, let me actually write this on the other side. Okay. What I'm going to write here is standard basis vectors give us another way to write a vector A, which is equal to A1, A2, and A3. Right, so they give us a new way to write that vector. And the new way is going to be to say that A, so this is A, but we can actually break this up as 3 separate vectors. So we can break this up as the vector A1, 0, 0, plus 0, A2, 0, plus 0, 0, A3. Right, so all I did here was break this up as 3 separate vectors. If we add all 3 of these together, we get back to what we started with. So it's the same thing. But now we can write this as A1 times 1, 0, 0, plus A2 times 0, 1, 0, plus A3 times 0, 0, 1. But remember, we actually had special names for these vectors, so I'll rewrite this as A1 times I hat plus A2 times j hat plus A3 times k hat. Okay. So all this is saying is whenever we have just any vector, we can always break it up as some number times the vector I plus some number times the vector j plus some number times the position vector k. Right, so that just tells us how much we have in each direction. So this is how much we have in the x direction, how much we have in how much we have in the x direction, how much we have in the y direction, and how much we have in the z direction. Okay, so example, if we have the vector 1, negative 2, 6, we can rewrite that as I minus 2j plus 6 times k. All right, so we can just rewrite that just only using this 3 standard basis vectors. And let's just do one more example here. If we have the vector 3, 4, so this is in 2 dimensions, we can rewrite this as 3 times I plus 4 times j. Okay. Now, let's move on to example number 5. Okay. So example number 5 is going to say if A equals I plus 2j minus 3 times k, and B equals 4 times I plus 7 times k, express 2a plus 3b in terms of I, j, and k. Okay, so they've given us 2 vectors. They've decomposed it for us into I, j, and k, and we want to figure out what this new vector is going to look like. So let me use a different color. We're going to have 2a plus 3b. And you can try to work this out on your own, but what we're going to get is going to be 2 times our first vector, I plus 2j minus 3k, plus, here we're going to have 3 times our second vector, 4i plus 7k. Right, so now we just need to multiply everything out and combine like terms. So if we do that, we're going to get 2 times I plus 4 times j minus 6 times k plus 12 times I plus 21 times k. And then we just combine everything. So if we do that, then we're going to get 14 times I plus 4 times j plus, so 21 minus 6 That's going to be 15 times k. And that's going to be our answer there. Okay. So I'll write here as a definition a unit vector is a vector whose length is 1. Right? So if we have a vector of length 1, we're going to call it a unit vector. So we've actually already talked about 3 unit vectors. And it turns out the 3 unit vectors that we've already talked about are exactly I, j, and k. Right? So I, j, and k are all unit vectors. Right, so if you see the name unit vector, that just means a vector of length 1, and we've already talked about 3 of those. Okay. So now we need to talk about how we can actually get unit vectors just from any vector. So the way we do that is if A, or vector A, is not equal to the 0 vector, so we're saying A is not equal to the 0 vector, then the unit vector in the direction of A is U equals 1 over the magnitude of A times A. Right, so we multiply A by 1 over its magnitude, and what that does is you're dividing the magnitude of A by the magnitude of A, so you're just going to have magnitude 1 whenever you do that. And magnitude is the same thing as length. So whenever you do that operation, you're going to get a vector of length 1. So I'll draw a picture of what this looks like. This might be a little bit small, but let's say we have our vector that we're starting with, our starting vector A. This is our starting vector A. And we want to make it a unit vector. So what we do is we divide it by its length. And then what we're going to get is going to be a vector that has its endpoint on the unit circle. So I've just drawn one quadrant of the unit circle. And the vector we get is this vector U that has length 1. But it's going to have the same direction because all you've done is divided it by a positive number. So this blue arrow is going to be our vector U. Okay. So we just take our vector, we divide it by its length, and we get a unit vector, meaning a vector that lies on the unit circle. So let's go ahead and do our next example. Put this down. Okay. So example number 6 is going to say find the unit vector in the direction of the vector two times I minus j minus 2 times k. Okay, so we're trying to find the unit vector in this direction. And let me go ahead and write that the size of 2I minus j minus 2k equals So we're trying to find the size of the vector because we need to, in order to get the unit vector, as we said earlier, we need to divide by whatever this number is. We need to divide by the magnitude of the vector. So we need to figure out its magnitude. So I said earlier, the magnitude of the vector, you just take each component, you square the number, and you add them together, then take the square root. So we're going to take 2, we're going to square it, plus our -1, we square it, plus our -2, we square it. Right, so all I'm doing is our vector, this notation means that our vector is this. This is our vector representation. So they've just written it in terms of the standard basis vectors, but they're the same thing. And we're taking each component, and we're trying to find the length by doing that. Okay. And now, let me erase this. Now what we have, we just compute this. This is square root of 4 plus 1 plus 4, square root of 9, which is 3. Right, so the length of this vector that we started with is 3. So our unit vector is going to be 1/3 of our original vector. Our original vector was 2i minus j minus 2k. Right, so we take 1/3 of this vector, and that's going to be our unit vector. It's going to lie on the unit circle, the terminal point. Okay. So now we just divide everything by 3. We're going to have 2/3 I minus 1/3 j minus 2/3 times k. Okay. So this is going to end up being our vector. Okay. So this actually has. Let me erase. Let me just flip it over. So all these vectors definitely have applications. And one of the applications I'm going to say is in physics. Right, so calculus was actually invented by Isaac Newton to describe physics, to describe our natural world. So I'll say here, one example is if several forces act on an object, the resultant force is the vector sum of these forces. Right, so in physics we often have pictures. Let's say we have a block that's moving down a ramp, then it's got friction, that's one of the forces. Another force might be, maybe it's also being, trying to be, let's say we have this picture. Right, so I'm going to erase this in a second. You don't need to write this down, but let's say we have a box on a ramp, then gravity is pulling it in this direction, or friction is acting against that. Let's say that there's some, let's say that this is actually a magnet, and the other side of the attracting force is up here, then the magnet is also pulling it this way, and there might be some other forces that we're not taking into account. And the way you find the total force is just by adding together all the vectors, and that actually gives you the force, right? So vector addition definitely comes up in physics, as it does in many other areas, so it's certainly very important. So I'll say that. And a fact, let me write this down. Fact if A has positive magnitude, here, this is the magnitude of the vector, and makes an angle theta with the positive x-axis, then so let me draw a picture of what's going on. So we've got our coordinate system here, and we've got a vector. So let's say we have a vector here, and it's making an angle theta with the positive x-axis. And let's say we have a point at the end. Let's say that this point is P. Let's call the vector A. Then A is actually going to be equal to the magnitude of A times, so if we divide a vector by its magnitude, we said it lies on the unit circle, and if you remember from trigonometry, the x value on the unit circle of this point is going to be the cosine of this angle, and the y value of this point is the sine of this angle. So this point here has, let me write this down here. So our vector A is going to be the magnitude of A times our cosine theta times I plus sine theta times J. Right? Again, the reason for that is because for a point on the unit circle, its x coordinate is cosine theta and its y coordinate is sine theta. Then you just scale it by the magnitude. Then all of a sudden you've got the original vector A. So I'll say that this point is going to be, this is going to be the x coordinate, cosine of theta times whatever the magnitude is. So the x coordinate of the point is the magnitude times cosine theta, and the y coordinate is going to be the magnitude of A times sine theta. Right, so that's going to be our point. Okay, so the important thing here is this statement. For any vector A, we can break it up as this cosine theta times I plus sine theta times J times its magnitude. And that's actually going to give us the correct answer. Okay, so lastly, we want to go ahead and use this to do an example. So example number 7. And this is kind of a long setup, so I'll write this down here. A woman launches a boat from the south shore of a straight river that flows directly west at a speed of 4 miles per hour. Okay. She wants the boat to land directly across the opposite shore. If the speed of the boat is 8 miles per hour, in what direction should she steer the boat? In order to arrive at the desired landing point. Okay, so this is our setup here. And we want to try to solve this problem. So let's say, well, we're given a velocity. So note, we're given a velocity which is going to be in distance per time. And it has two parts. It has both direction and magnitude, which is saying, so the direction is which way it's going. Sorry, I miswrote this. It's which way it's going. So the reason we know which way is it says the boat is going, sorry, not the boat, the velocity of the river. The velocity of the river is 8 miles per hour in the direction of west, right? So we're given the direction, and the magnitude is the speed at which it's moving, which is 4 miles per hour. So this is how fast, right? So we can actually represent that as a vector. So that's our goal here, is to use vectors to solve this problem. So let me use blue to represent the river. So this is our river. We said it was perfectly straight. And we know that we want to get to this point, or let's say we start at this point, and we want to get to the point that's directly opposite that point on the other side of the river. Okay. And we know that we can represent the velocity of the current as a vector, right? So we can represent that as a vector, and it's going west. So north, east, south, this would be west. So we can represent this as a vector. So this is the velocity of the current. And we want to draw the velocity of our boat. Well, we're going to need our boat to go somewhere in this direction. This is our velocity of the boat. Mind you, it should be double the speed of the current. So I'm going to draw a pretty long arrow there to notate the fact that it's kind of a lot bigger than the speed of the current. It's twice the speed. And it's going to be at some angle theta. So we're going to need to drive this way with our boat in order to counteract the current to get us to land exactly opposite on the river. Okay, and now we're trying to figure out what this angle has to be, right? So it's asking what direction she should steer the boat. So we're trying to figure out this angle. So I'll say here, we want to get to this point. We're starting at this point, and we want this to be our velocity vector, right? So we want to exactly counteract the current. So I'll say here, the current flows directly west at 4 miles per hour. Okay. So it flows directly west at 4 miles per hour. So what that means is the magnitude of the vector for current is going to be equal to 4, right? And it's actually in the west direction, so we can say that the magnitude is going to be -4. It's in the negative direction. Okay. And now our vector for current is going to be equal to this magnitude of -4 in the I direction, meaning the x direction, because I is the x-axis, so it's -4 in the x direction, And we can ask ourselves, does it have any y component? Meaning, does it go up and down any amount? And we can look at the vector and say, well, no, it's directly west. It doesn't have any vertical component to it, so the next part is plus 0 times j hat, right? So that's our vector for the current. And I'll write here, the label that we use for the boat is going to be v sub b. We're using b for boat, right? So this is going to be the vector for the boat. And I'll write that down over on the left side here. Okay. So let me get this. So the boat moves at, we said the speed was 8 miles per hour. So the magnitude of the boat's velocity is going to be 8. So we can say that the velocity of the boat is going to be equal to 8 times, so we know the magnitude is 8, and we said earlier on the other page, let me flip back to what we had. We said that we can represent a vector, no, I erased that part, sorry. But we said we can represent a vector. Let me just rewrite what I wrote. We said we can represent a vector by the magnitude of the vector times cosine theta times I plus sine theta times j. Right, so we said that we can represent any vector in this form. So we know the magnitude was 8. And we know this part is going to be cosine theta I plus sine theta times j. Right? So this tells us that we can write our vector in that form. And that's what's going to be helpful here. Okay. So our next part of the problem is going to be to say the resistance velocity, sorry, not the resistance, the resultant velocity, so that's the vector v that we drew. The resultant velocity v is the sum of v sub c plus the sum of v sub c and and v sub b. Right? So if we add the two together, we're going to get the total velocity, right? So there's two velocities acting on the boat. It's the speed of the boat, so it's the engine or the motor. You got the velocity due to the motor, and you've also got the velocity of the current, right? So if you add together the two velocities, that's the total velocity of the boat. So we just have to add those two together. So i.e. v equals v sub c plus v sub b. So v equals 8, so v sub b was 8 times cosine theta I plus sine theta times j. And we already saw what v sub c is. V sub c is going to be minus 4i. Right, so that's what we have. And if we can go ahead and combine what we have, then we're going to have 8 cosine theta minus 4 in the I direction plus sine theta, or sorry, 8 sine theta in the j direction. Right, so I just combined everything. And that's what we get. And now we have to think about what we want for our resultant velocity. We want that the horizontal direction, you can ask yourself, how much velocity do we want in the horizontal direction if we want to end up exactly across from where we started at? Well, we're going to want 0 horizontal velocity, because otherwise we're going to get either skewed this way or skewed this way. So we want the horizontal part, which is this part, so we want 8 cosine theta minus 4 to be equal to 0. Right, so we want that to be equal to 0 so that our horizontal component is 0. Now we just have to solve for theta, and then we're done. Right, so we want cosine theta equals 4 over 8, which is the same thing as a half. And then now we just need to solve for theta. We know cosine theta is a half. If you want to figure out when that's true, I usually just use the unit circle. Let me use a different color here to not mix it up with what we've already written. So if we want to draw our unit circle, so they teach 2 different ways. They teach either using the unit circle or the special triangles. I usually use the unit circle because it looks hard to remember. There's actually an easy trick to remember, right? So if you go 1, 2, 3, then 3, 2, 1. You take the square root of everything, but the square root of 1 is just 1. And you divide everything by 2. And then now the final step is to turn everything into a point. Right, so my drawing might be a little bit hard to read. But you turn everything into a point, and now this first angle is pi over 6, the second angle is pi over 4, and the third angle is pi over 3. And the reason why the unit circle is useful is because you can just read off the values of sine and cosine. So here we need to find which angle gives us that the cosine is 1/2. The cosine is the x-coordinate on the unit circle. So we look for 1/2 in the x-coordinate. We see that's up here. So we know the angle is pi over 3. So we know here that theta equals pi over 3. And if you convert that into degrees instead of radians, you don't have to do that, but if you convert that, that's going to be 60 degrees. So this angle here is exactly 60 degrees. This angle needs to be 60 degrees to exactly counteract the current. And that's going to be our answer. The angle that the boat has to move at is 60 degrees from the shoreline, from the positive x direction, so from this shoreline. Okay, that's it.